All right, so we got final 2 tests for the semester before the exam. This Wednesday, you have your written test 2 right here. You got a guide, you got example questions. So we managed to just schedule an in-person review session. If you can make it, you'll be great. You'll be tomorrow, 3 p.m. in the Ross Building North. You can check the e-class for, again, the detail, right? But you can look at the map as well on the campus. Should not be too difficult to find. I'll be there, the TA will be there, and then we'll be ready to answer your questions. And I will definitely try to record a session and also try to make it available. But since I also got other classes until 7 p.m. on the same day, I'll try to make it happen, hopefully by 9 p.m. for you, or maybe a little bit later. But it might be the best if you can just attend the session earlier and ask questions, clarify things, before, later. Anyway, so I'll leave the choice to you. Optional, okay? Tomorrow in person, okay? Right here. And then the notes about typecasting the PDF, I kind of showed to you guys last Wednesday, so please also take a look. You can also help. And just like the midterm course evaluation, so this is the final one, official, right? So you can follow the link, and then for early participation, we got the same bonus scheme as last time. So again, it's optional. If you want to leave some comments about teaching, learning experience, you'll be most welcome. It's completely anonymous. I will not see any result until the middle of January, so definitely cannot know anything about it. All right, so definitely feel safe to put it down. Okay, I'll try to give you some reminder a little bit later, just so that you wouldn't forget. All right, guys, any questions? About your programming test 2, yes, we are gonna do the grading pretty soon, and then I'll aim for maybe this Friday, late Friday. If no, I'll definitely try before Monday's class, and then give you the result and the feedback, and we'll talk afterwards. All right. Okay, let's do a quick recap, and then I expect to do 2 more lectures on inheritance. I think we already pretty much have done the foundation of that, so now it's more like a natural extension and some more exposure to different context to see the inheritance. You guys have done a lot on the conceptual learning, but now it's time to really pay it off, right? We'll see. Okay, let's do a very quick recap. Oh, just a quick reminder as well. So your written test number 2 tomorrow, sorry, not tomorrow, Wednesday, will be up to and including slide 67, right? That's something already confirmed on the guide. Just want to be sure. And then what I'm gonna cover today is not gonna be covered on Wednesday, but somehow they can be a nice review as well, certain parts. Okay, let's do a quick recap. So last time we basically started off by motivating about the usefulness of doing a typecast, right? So whenever you got some reference variable, dynamically you know what it is really pointing to, but somehow you cannot really just use a reference variable to call the method, simply because static type defines the expectation. And we know that it's somehow something called undecidable problem. For this page here, the way I kind of phrase it as an ACE+ challenge simply tells you that theoretically it's not possible to keep track of the dynamic type, just the way I phrase it. But you don't really have to dive into any details about why it would be an undecidable problem, just beyond the scope of this course. I just try to connect beyond this course just for your knowledge, right? Just know that the compiler of any sort, Eclipse, Visual Studio, IntelliJ, they simply cannot keep track of the dynamic type. It's just theoretically impossible. So what we can do as a workaround is by using typecast, right? We have done lots of examples last time. For the recap, I just want to mention 2 things, okay? So you want to get back to this diagram here, right here, right? It's a very important diagram. It looks a little bit complicated, but just the way it is. You have to know about this many details. Whenever you have a variable declaration, as soon as you declare your variable, let's say my phone to be Android right here, you can do typecast in the following way that will compile. Either you can do upward cast to one of the ancestor, including itself, or you can do downward cast to any of the descendant classes, including itself as well. So that's what we call compilable cast, in which case you only consider the static type, nothing about dynamic type just yet. That's dimension number 1. Right? Keep that very clear for Wednesday as well. And of course, if you're doing neither upward nor downward tasking, sorry, let me see that. If you're doing neither upward nor downward casting, in which case it would be non-compilable, right? It just wouldn't compile. What about for those typecasts that will compile? Are we gonna run into the so-called class cast exception? So here is the principle. When I try to cast my phone into certain type, in which case I'm really talking about can the current dynamic type for the variable fulfill the expectation of the type I'm trying to cast to. For example, can I cast right now from my phone down to Galaxy S21? That one, I cannot do it because dynamic type Samsung cannot fulfill Galaxy S21. In order to fulfill, Samsung must be a descending class of the cast type. Right? That's pretty much the essence of what we said last time. So really try to review about these 4 categories and then get used to it. All right. So guys, any questions about the 2 dimensions, compilable versus non-compilable, and also class cast exception versus exception free? That's what you need to know for Wednesday. All right. All right, I still have my office hour today. If you want to drop by and have some chat about any confusion, you're more than welcome to. Or approach me after class. I can also stay a little bit longer if that's needed. So let's now, that's also important exercise here. We basically say you can cast from one type to another type, just putting upward cast and then downward cast. Right? Also revisit the idea as well, okay, the detail. All right, let's now talk about something new but still relevant. Let's now move on a little bit to say, well, I know that even if my typecast is going to compile, I might still run into like a class cast exception if I'm not being careful about what my dynamic type is. So there is an operator in Java that can help you solve this problem somehow at the runtime. It's called instance of operator. So that's something we're going to talk about today and then do lots of examples again. Right, let's now just start with some summary about the instance of, and then we'll do examples. So the syntax you're going to learn for this one here is going to be an operator called instance of. Instance of. It's a single word. Okay? Instance of with no space in between. Single word. And it's a binary operator. It's going to take something on the left. It's going to take something on the right as well. All right? What appears on the right is always a class name right here. So it's going to be a class name. And let's say for now, let's call it Y, the name, okay? Just a class name. And then on the left-hand side, it's going to be some expression. It's going to be an expression denoting some objects, okay? So example could be, the simplest one could be, you just say, for example, I might say X. X might be a declared variable somewhere, like a my phone, or maybe RS, right? Like a variable. You will see also example later, could be array indexing expression. I might say array A, and at index, for example, I. I is maybe some index value, right? So this is just another expression, right? So left-hand side can be any expression that represents some objects at the runtime. So let me just put X right here. All right, so now there are 2 things for us to know. Compiler time, behavior, whether or not it will compile, and also at the runtime, what's going to happen. Let's talk about compilation time, which is something we know just from last time. Okay, let's start with this. This instance of expression will compile as long as casting X to Y is a compilable expression. I'll write it down first. Okay. So this instance of compiles if and only if, right? Basically, so if you can say either way. Okay, instance of will compile if and only if the expression y x is compilable. And we know pretty well for this expression to compile, it should be either an upward or downward cast. Okay, it's about compilation. So this one here, so the way we define the instance of being compilable is just using the corresponding typecast expression, right? And you know pretty well from your study for Wednesday, all right? That's about compilation time. What about a runtime? At a runtime, assuming that it compiles, let's be careful here. at a runtime. Oh, just before that, let's try to understand what instance of is a little bit vague about what it is really trying to say. I would say let's go consistent with our intuition so far. Rather than thinking that it's instance of, thinking about in the following way. Okay, I'll put it here. Can X dynamically fulfill the expectation of Y? That's what it is trying to say. All right? Can dynamically fulfill the, okay, I'll try to see if I can make this a little bit down. Yes, I can. Dynamically fulfill, okay, sorry, let me write it again, so that'll be less messy. Can dynamically fulfill dynamically fulfill the expectation of, right? If dynamically X can fulfill the expectation of Y, in that case, we're going to evaluate something. That sounds like just like the condition for having a class cast exception, but we'll get there a little bit later. Okay, but that's one intuitive way you can think about. Okay. All right. So at the runtime, if the instance of expression actually compiles, at the runtime it's going to evaluate to either true or false. It's a Boolean expression. So let's now put it down. Evaluates to Boolean. Either true or false. All right? And what does true really mean and what does false really mean? Of course, they are the opposite to each other. Let's talk about what if it is true. Okay? So we talk about if true if, we can write in different ways, but let's write them down. Dynamic type of X can fulfill the expectation of Y. That's the most intuitive notion to really understand instance of. Okay? Meaning that if we cast X to Y, we wouldn't get any class cast exception. You can just say consequently, right? Okay, that's one way to put it. Number two, you can say dynamic type of X is descendants of Y. Because dynamic type of X is descendants, of course it will fulfill, right? It follows logically. Another way to put it if you want, you can also say Y, conversely, is an ancestor of X dynamic type. Okay, so 1, 2, and 3 are equivalent to each other. But I would suggest always try it with number 1 first, which will be intuitive and it's harder for you to get wrong. You want to think it through about number 1 and then 2 and 3 will just follow afterwards. And what does it really mean when E evaluates to false? Okay, let's also write it down as well. Oh, actually false just otherwise. Okay, so think about over here, false otherwise. If it cannot fulfill or it is not descendants, in that case it will be false. Right? We'll see example. And let's say a little bit more. What would be the consequence of being true? In that case, what can we do about it if this expression happened to be true? If I evaluate this particular expression at the runtime, it tells me that's true. What can I do then? That means here, if true, then it is safe to execute the cast from X either up or downwards to Y without any class cast exception. So when I say safe, that means it's class cast exception free. Okay, so safe over here is simply means class cast, no class cast exception. Okay, and that's the typecast that we can do. All right, any question about the instance of operator? It's a binary operator. You have to put left and right, but the left and right are different things. The best way to understand, I think, will be to think about the left-hand side can dynamically fulfill the expectation of the right-hand side. Think about that way, and then you can go also apply what you learned from before about the typecast. And what's so useful about this operator? So you, as a programmer, you don't really want to rely on your tracing ability so much, especially when things get a little bit complicated. You always somehow want to do a little bit of check before you can do some typecast. So I'll show you some example. To what extent you want to really do an instance of check before every typecast, you have to reach a balance. You don't necessarily have to write a single X instance of Y whenever you want to do a typecast. That would be a little bit kind of overkill. You don't want to go excessive. You have to strike a balance. Exactly what should be a balance? You will need to gain some experience on programming. So that one I cannot teach you, right? You gotta gain some experience maybe beyond this course. But at least we can analyze if you got typecast with the instance of, what will be the consequence? What kind of a safety guard are we really implementing here? All right, let's take a look. Okay. Just say one more thing. Okay, I can visualize something here quickly. It's on my notes. So let's say we got X over here, right? X dynamically is pointing to some dynamic type. So you can think about this will be X's dynamic type. And you can think about the Y here can be some potential cast type, potential. Visually speaking, we want dynamic type for X right here to be a descendant of Y, so that it can fulfill its expectation. So you can visualize to say in the hierarchy, if this is one class, then Y should be one of its ancestor. For example, if you go through the ancestor path all the way, you should really reach maybe Y at some point. Okay? Visually, that's what it means. Not the other way, of course. All right, any questions? Before we see, before we see some example, I would like to do one more conceptual summary. Okay. Actually, you know what? Why don't we do example right away? Sorry for changing my mind. I think that'll be better. Before we do this generalization, let's do one example right away. Okay, let's consider what we are mostly familiar with. Okay, in this example here, let's remind ourselves quickly. Okay. So here, Jim has the static type students. Okay, so this here is a student class. It's a static type. And dynamically, it's a non-resident student at the moment. Okay, non-resident students. So that one there is dynamic type. But if you feel more comfortable by visualizing it, just go ahead. It doesn't take long to do it. Okay, let's see if we can do it without having to draw. And then you can see that we have some instance of check right here. For now, just disregard this line, just for now. Pretend it's not there, okay? Let's only look at these two lines right here. Only these two lines, okay? As far as compilation is concerned, you can see right here, this typecast over here, right? You can remind yourself, Jim has the static type students. And then when we try to cast to resident students, we're basically trying to cast to resident students. So this is the cast type. And we know that as far as the compilation is concerned, from students to resident student, downward cast is going to compile, right? However, we're going to run into class cast exception. Agree? Let me write it down. Okay. You can think about so far, it's still more like a recap about what we should know for Wednesday, right? So this one, number one, it compiles because it's a downward cast. Downward cast. Number two, anybody would like to try? Why would this run into a class cast exception? What would be the justification you will put? I'm already telling you there's going to be a class cast exception. But can you explain why? As complete as possible. Go ahead, please.
The attributes are incompatible. There's between non-resident student and resident student.
Okay, I think definitely on the right track. You're saying from non-resident student to resident student. But somehow I want to be a little bit more complete right here, right? That's okay. I think you guys are still getting used to it. So what I should really say is, it's going to be a class cast exception because dynamic type of Jin, which we know is non-resident students, cannot fulfill the cast type, which is resident students. Cannot fulfill because this is not a descendant class of that, period. All right? So my point is, if we did not have this line, for example, just do what we did from Wednesday, you're going to run into class cast exception. All good. Okay? Good in the sense that we understand what we're doing. Okay? Now, what's going to happen if we have this additional layer right here? Why would that be considered as a safety net? This is something we're going to learn today. Okay? Let's now highlight this line here and try to study that. So, right here. Okay, line number 2. So line number 2, we're basically asking the following question. Oh, again, let's now also say 2 things. Number 2, should line number 2 compile? Right? We talk about what does it really mean when instance of expression compiles. It will compile if casting Jin to resident students will compile, which we know is a downward cast. So number 1, the instance of expression compiles because casting Jin to resident students compiles. Right? That's something we already explained. Number 2, at the runtime, when we try to evaluate this, is it going to return true or false? In this case, we're basically asking, can the dynamic type of Jin, which is non-resident students, fulfill the expectation of the cast type, which is resident students? Can it? No, it cannot. False. All right? It's going to evaluate to false because Jin's dynamic type is not a descendant of resident students, which is right here. And of course, you can see that normally when you want to use the instance of whatever this type is, if that one happen to be true, you want to use that type verbatim right here for the cast. That's really the point about doing the safety check. Right? It's going to evaluate to false. So that would mean right here, given that this is going to evaluate to false, right? So number 2 over here, we know that is going to evaluate to false. That would mean these 2 lines, which is part of the branch for the if, is going to be completely bypassed. Bypassed. Meaning that the potential class cast exception prevented. Okay, let me recap, and then I'll take questions. We started by disregarding this check right here. If we only consider these 2 lines, we know that we're going to get class cast exception at the runtime, like what we learned from last week. And then by adding this new construct that we just introduced today, it's basically asking the same question. Can Jim dynamically fulfill resident students? In this case, dynamically, Jim is non-resident students, which is not a descendant of resident student. So it's going to return false. In that way, this thing here is going to give us false, so we are not going to execute any of the branch in this if. So we're going to go just to the next line, basically. Right? We're going to prevent the class cast exception from happening. All right, question? I hope that's clear. All right. If this is clear to you, definitely try another example here, which is going to be the similar argument pattern. I'll put that as an exercise for you. You can also see the solution on the slides. Okay, exercise. And the best way to really solve this will be try not to really visualize as much. Maybe you can just simply try to annotate the inheritance hierarchy to see where things are. That might be a better way you want to get used to solve questions more efficiently. Okay, great exercise for you. Okay, okay, I'll pause a bit. Any questions before I try to generalize this? All good? Okay. Let's now talk about generalization, okay, which is not too bad, okay? So we basically consider 3 lines over here. Line number 1, in order for this to compile, B must be able to fulfill expectation of A. In which case, yes, because B is a descendant of A. That's how we start with. All right, so line number 1 is completely okay. So you can think about this one here is more like a static type, and this one here is like a dynamic type. Let's start with that. And then we want to do some instance of check. Can OBJ dynamically fulfill the expectation of this particular type? And this type here will be used verbatim as a cast type inside the branch, right? That's basically what we just did. I just make it a little bit more general. And then we want to ask about what can be the right question mark over here to really make sure we can actually bypass the check so that we can prevent the class cast exception. Right? That's really the question we want to ask. Okay? Let me start by line number 2, right here. Let me highlight it. Okay, again, I'm highlighting this one here. And let's remind ourselves about the definition intuitively. So this one here, we know that is going to be true if and only if OBJ's dynamic type can fulfill the expectation of question mark, right? That is something we just mentioned, right, when we first introduced the syntax. And given that it is true, right here, at this point, we know that we wouldn't run into any class cast exception, guaranteed. Because if we're able to get to this point over here, that means, okay, at this point, we can safely assume that OBJ instance of question mark evaluate to true. Otherwise, we wouldn't even reach that line, right? Logically, okay? And since we know that's the case, we can assume right here. And now let's look at this line here, okay? Let me say star, star, okay? Are we gonna get any class cast exception over here? That's a question, okay? Star, star, the answer is no, guaranteed. No class exception, class cast exception, guaranteed. Because the instance of expression evaluate to true, meaning that OBJ's dynamic type can fulfill the expectation of question mark. All right, so the final bit of arguments. If we're able to reach this line, given that we got some extra layer of check, we know that guaranteed there will be no class cast exception. All right, okay. And let me do a little bit more annotation, and then I can maybe take your question just in case. Okay, guaranteed. All right. So what can the question mark be then, right over here, right? You're basically asking what class can be fulfilled by B, any of B's ancestor, or any class for which B is a descendant, either way, okay? It could be B itself, or it could be any of its ancestor. You just go all the way to the top. So these are all the classes that will make the instance of true, in which case having a cast is not going to run into class cast exception. Okay? I'll put it down here. So all these orange classes here will be all these classes which are ancestors of OBJ's dynamic type, right? Ancestor will make the OBJ instance of true. That means no class cast exception at runtime. Okay. So now, so this question mark here can be replaced by either B itself or any of the ancestor. Then you'll be safe. No class cast exception, meaning that the instance of is just going to be true. So you can go ahead and do it. On the other hand, anything that's actually going to be not anything that's not ancestor of B, right? In that case, what can that be? Okay, let's put it down. So think about right here. Okay, I'm going to put it here. Okay, so think about right here. These classes. Okay, you can think about right here. These classes will be the instance of compiles, but evaluate to false. Because these classes are simply not the ancestor of B. Or you can think about B is not the descendants of them, in which case you just cannot fulfill its expectation. On the other hand, what about other classes right here? Like right here, this one here, and also this one here, and also this one here. You can think about these classes over here are neither ancestor nor descendants. Neither ancestor nor descendants of OBJ's static type. So that means the instance of will not even compile. Not even compiles. Okay, let me recap and then maybe I'll take questions. We start with this line of declaration over here, right here. And then when we want to see whether or not instance of is going to compile, try to think about whether or not we can compile by casting OBJ to this particular class. It will compile if there's either upward or downward cast. It will not compile if this class over here is neither descendants nor ancestor for the static type, right? In which case, look at this one here. The ancestor will be right here. The descendants will be actually right here. Oh, am I doing something wrong? I am. Okay, let me do it again. To really avoid, guys, let me start over just for this part. Okay, I'll put it here just to be 100% precise. Okay, let me just clear that first. Okay. Yeah, make sure that's clear. Just give me one moment. I'll do it again. Okay, let me also get rid of this one here. Okay. And also this one here, this one here, this one here, okay, this one here. Okay, let me do it again. And I'll clear this one here when I post the notes. Okay, let's annotate it here. So we got A and we got B. Okay, we got A here, and also we got B here. Okay, when we say instance of, so static type, dynamic type. When I write things like this, when I say A, obj equals new B. So now, when we talk about compilable instance of, when I say if obj instance of, question mark, okay? Let's start with this one first. In order for this one to be compilable, if question mark is either ancestor or descendants of A. Okay, so that means we can either go from, we can either go all the way here, which would be ancestor, and also all the classes underneath it. Right? That's either ancestor or descendants. So that will be compilable cast or compilable instance of. So all these classes will be compilable cast and instance of. Right? The only thing that's neither ancestor nor descendants is right here, right? With respect to A. So this one here is neither ancestor nor descendants. So that means non-compilable. Okay. And then we go further to the second dimension. Given that it compiles, we want to see whether the instance of is going to return either true or false. It will return true if the class can be fulfilled by the dynamic type, which will be only the descendants of B, which is right here. Okay? That one there will be either the B itself or maybe here and also here and here and all the way to the root right here. Okay, so these are all the things that will guarantee to give you true. So these are the classes that will give you instance of. So we got obj instance of that question mark is going to give you true. All right, finally, what about other classes over here? For example, right here, those are the classes which are not the ancestor of the dynamic type B. In that case, you're just going to get false from the instance of right here. Okay, all these classes. So all these classes will be not ancestor of dynamic type B. So that means the instance of return evaluate to false. Right, so compare this particular diagram over here with what we said last Wednesday, right here. So they are actually corresponding to each other, right? The only difference is for instance of, there's no class cast exception per se. At the runtime, it's only true or false. But whenever you say true, it's when you don't have the class cast exception. When it's false, it's saying you may have class cast exception if you try to go ahead with the cast. Okay? And I'll fix this one when I post the notes. Okay? It's not exactly accurate. And you can go with this one. That one's accurate. All right, any questions? Daniel.
Could you please reiterate when it compiles, like the first one?
The compile? Okay.
You circle the entire site.
Okay. So because somehow we choose a static type that's rather high in the hierarchy, right? So you can think about, given this static type, what can we do compilable cast? You can either cast upwards, which will be all the way to the root of the hierarchy, or anything that's A's descendants, which will include everything that's underneath A. So these classes will give you compilable cast or compilable instance of. Even the B, B is a dynamic type, right? Yeah, the pink one, yes. The pink one, okay, the pink one's over here is about when it compiles, it might give you class cast exception, right? So remember, we only talk about class cast exception in dimension number 2. But in dimension number 1, we talk about whether or not cast will compile, right? One dimension at a time. And for these classes over here, it's neither upward or downward cast, in which case you would not even get to the runtime because they wouldn't even compile. Okay? So I'll say, think about the compilation here for instance of and typecast together. They really are exactly equivalent to each other. Yeah. Okay. Right. Why don't we do some quick example and then we'll take a short break. Okay. All right. So this will be exercise, and then let's now do some quick check for instance of. Right. Just and I'll do that efficiently. So we don't need to visualize anything. We just have to see how we can deal with compilation, well, just a runtime, okay? So here again, we got a line of decoration right here, okay? So what we have is my phone actually got static type smartphone, static type. And also we got Samsung, which is dynamic type, right here. Okay, we fixed these two. And then we have the instance of check. And the left-hand side for the instance of, we make it the same. They're all my phone. Okay? As far as compilation is concerned, all these instance of check will compile. Because relative to the smartphone right here, all these guys will just be like a downward cast. So that's why they all compile. All right? Okay, let me just put it here. All the instance of check, all instance of compile. Because the right-hand side is descendants of the static type smartphone. It just happened to be at the top. Okay, so all compile. But what about at a runtime? Are they going to evaluate to true or false? Right? So let's now think about it. It will give us true if dynamically my phone can fulfill this type over here. So let's say just for the very first one, can my phone dynamically, Samsung, fulfill Android? Yes? No? Yes, right? Because Samsung, descendants of Android. All right? Okay. So now this one here is going to give you true. So now, can Samsung fulfill Samsung? Of course. Next question. Can Samsung fulfill Galaxy S21? No, it cannot. Because Samsung is not a descendant of Galaxy S21. All right? So that one there is going to be false. Next one. Can Samsung dynamically fulfill iOS? No, because Samsung is not descendants of that, right? Also false. Finally, can Samsung fulfill iPhone 13 Pro? Also no, right? Once you see where they are in the diagram, it should be obvious. So to really solve this exercise here, again, there are two things over here. Number one, we're looking at whether or not the instance of operator is going to compile. To see that, you have to look at the static type of this guy here, which is smartphone. And think about just either you're doing upward casting or downward casting with respect to the class over here. Right? It's either way, because this static type just happened to be at the top. So again, you're always doing downward casting. On the other hand, when you want to figure out whether it's going to return either true or false, you want to ask yourself, can the dynamic type over here fulfill the expectation of the right-hand side of the instance of? In which case, this Samsung here must be a descendant of whatever type you put over here. All right? It could be a little bit overwhelming, but you can get a big picture and you may have to revisit this point here, right? Just to get a little more fluent. Okay. Okay, one more and then we'll take a break. Okay, it's a bit later than usual, but let's finish this one here quickly. So now, given what we have got from before, all right, again, let's now look at the static type right here. And we got a dynamic type right here. Okay? So static type is here. Dynamic type is here. Samsung. So now we got 3 instances of check right here. And followed by some cast. So you can see this is 1 instance of check. This is 1. And there is another one right here. One thing to see. We can see here the type we're doing Samsung here. We're using it verbatim for the cast type. And also for Galaxy S21 Plus, we're also using it verbatim as the cast type. And similarly for this one here as well. That's really intentional. Whatever you check for instance of, if that's true, you should really use that for typecast. Okay. So now let's take a look. This one here. We know that Samsung, my phone dynamically is Samsung, which can fulfill Samsung. So this one here is going to be true. It's going to be true, and then this particular typecast is not going to have any no class cast exception, because that's true. On the other hand, let's see Samsung cannot fulfill Galaxy S21 Plus. So that means this one here is going to be false. This one is going to be false. So this one here is going to be bypassed. So we don't really have class cast exception accordingly. So we really got a safety check working. Okay, final one. What about this one here? So here, dynamically, Samsung can fulfill Huawei right here? No, it cannot. So we're going to get false as well. So this one here is also going to be false. So that means this part here is going to prevent the class cast exception. All right, questions? All right, so why don't we take a short break and take attendance, and then we'll continue with more. All right, just one more set of examples about typecast, instance of, maybe not instance of anymore, just typecast very quickly. And then we can move on to another topic to really relate inheritance with callback value. That's something we'll do. Okay, let's look at this set. Okay. Again, we have some variable declaration here, and here we're only worrying about compilation. Okay, so we only look at a static type. So we got smartphone right here, right here. Even though dynamically it's pointing to iPhone 13 Pro, doesn't really matter. We're only talking about compilation. Okay, we're basically asking for all these method call, are they going to compile or not? Right? We just check for compilation. Okay. So you want to start by asking yourself, if I declare SP to be smartphone, I can only call smartphone methods on that, which will be either dial or surf web. Anything else will not be compilable, right? So only dial and surf web. But for FaceTime and QuickTake, they don't belong to there. Doesn't matter what dynamically the type is, right? So that one there is just going to be, this will compile, but the other two will not compile. You only consider the static type only. Even though dynamically, it might support the method. Doesn't matter. You only look at the static type. All right, next one. Let's say we have another declaration here. Let's say iOS. A little bit lower in the hierarchy. That means it might allow a little bit more expectation because it's lower. And for iOS, we know that it's going to support FaceTime and also surf web and also dial, right? It can accumulate all the expectation. So now it will be dial, surf web, and FaceTime. So dial, surf web, and FaceTime. But for the QuickTake, no, it's not going to compile. Because statically, iPhone right here is just iOS. That's all you got to consider. All right. And then, next one. So let's now say this time we try to make the static type and dynamic type just the same. So we try to get as much as we can really call on these objects. So now in this case, iPhone 13 Pro is right here. Right? So we know that the method that we can call will be over here, QuickTake, also FaceTime, also dial, and also surf web. So these are the only four, nothing else. Okay? So dial for sure, FaceTime yes, and also quick take yes. But if you put any methods outside the ones we just identified, it's not going to compile. Okay. Again, you only look at the static type for the context objects. Static type is iPhone 13 Pro. Okay. So you can definitely consider compare 3, 2, and 1 to see why certain methods will be callable on the reference variable, but some of them will not be. It's really because of static type, right? That's really the point I'm trying to emphasize again. Okay, this one here kind of just show you the anonymous cast expression. Okay, so let's take a look at this. If I only look at this expression here, just this one, so this is a typecast. So this is a typecast expression of static type corresponding to the cast type. iPhone 13 Pro. And of course, in that way, we can call all the dial, FaceTime, and quick take. All of them will be okay. Right? Just like an anonymous cast. So the main point we are revising here, or revisiting here, is just about what's really the static type whenever you have some cast without a name. That's also something we said earlier. Okay. Okay, let's now move on. Okay, final one. And this one here, very similar. So here, again, we have some instance of check right here. So we're saying that dynamically can S fulfill the expectation of resident students. If we're able to get to this point over here, that means it is true. In that case, we can do two things over here, right here. Okay? We can definitely do the casting. You can think about this cast over here will be okay without any class cast exception. Class cast exception free, guaranteed. Because the instance of check is actually true, guaranteed. All right? All right, questions? Yeah, maybe try to after Wednesday or before Wednesday's class, if you can revisit about the principle of instance of and try to connect that to typecast, that might be good. If you find it totally confused between the typecast and instance of today, I would say forget about instance of until Wednesday. You may want to focus on your test, but maybe after Wednesday, you really want to connect these two together. They are really relevant to each other, the way I put it. Okay? It's going to be important for your exam. Okay? Guys, any questions? Okay, we got basically 3 more small topics to cover for inheritance. One of them will be polymorphic callback value. Another one will be polymorphic return type. And the final one will be just to see some overridden equals method a little bit more in the context, right? Let's see these 3. I might just be able to do partially number 1. Let's see. And before we talk about it, I can tell you the slides that we are starting to cover. So today we basically talk about everything to do with the instance of. You can also go over the slides later when you study for your exam. Okay, so now we're going to start from slide number 77. Okay, so this is where we're going to start from. Okay, 77. Okay, but before that, I would like to remind all of us about callback value. Right here. Okay, let's remind us about callback value and see why inheritance might have a role to play in the callback value. Okay. Okay, let's now do some sketch over here. Callback value. Right here. Okay, we have a caller, we got callee, right? Let's say on the caller side, we have some fragment of code. And for the callee side, we also have a fragment of code defining some method, caller. Okay, caller and callee. Let's start on the caller. Excuse me. So let's say we have a class called C. And then we have a method, let's say M. Let's say it's a mutator, doesn't matter. M. And then let's say we have some parameter here, reference type. Let's say the type is symbolic, T1, okay, some type. T1. And then some param. And then inside, you can actually do some coding, right? And let's say on the caller side, we are trying to create some instance of C. So C obj new C. And then let's say we define some argument. Let's say T2, okay, a different type potentially. Let's say we got T2, and then we got some arguments. Will be some initialization, and then here we got the method call, which is going to define the caller and callee, right? Obj dot m, and then arguments, okay? Now, call by value. Do you guys recall what exactly is the implicit assignments that we're having? Is it going to be param equals arg or arg equals param? Which one? You guys remember? Daniel. Yeah, that's right. Okay. The order is important because if you get order wrong, then you will get this rule of substitution wrong, applying the wrong way. Let's now take a look. Okay. We're basically connecting these two lines by call by value. Okay, let's remind ourselves, call by value tells us there will be some implicit line even before we execute the very first line of the the callee method. It's going to be param assign arg. Okay, param and also arg right here. And then we got equals. And we learned about rule of substitution. So that's exactly the point that we have to now apply the rule of substitution, right? How do we apply that though, right? We said before, in order for this variable assignment to really compile, we got to look up the static type on both sides. Look at the static type for param, which will be T1. Look up the static type for arg, which will be T2. And there's got to be some relationship between them. Right? So let's now take this one here. So we now recall the rule of substitution. Right here. Okay? Anyone would like to give a try based on this visual? Daniel, go ahead. Give me one. Which type? Which type? So we talk about T1 and T2, right? So type 2? Yeah, I agree. So T2 over here, T2, the static type for the right-hand side must be descendants of the static type for the left-hand side, right? You can say T2, a descendants of T1. Or intuitively, you can think about T2 fulfills the expectation of T1. You can go either way, right? So what we're going to talk about right now is about method call. You just have to remind yourself about the variable assignments you're doing between the caller and the callee, and everything else will just follow through what we learned about the rule of substitution from before. All right, let's now do some example. Okay. All right, so this is the first time that we're going to put inheritance in combination of array. But it's not too bad, right? Just let's do one thing at a time. Line number 2 is when we declare an array of students, and then we call it SS. Okay, I'll start from here. Okay. So if you start from here, let's only look at that, right? The declaration. Just look at that. So what we have is, so it's declare type. So think about the students over here means So this is a static type of each elements in the array. Static type. Dynamically, we don't know. But if you kind of somehow apply what we learned about polymorphism, dynamically, it could be any descendants of students, basically. That's something we'll touch upon maybe on Wednesday. Okay, so based on this, so this question here we can answer right away, right? You can think about S is 0, the first element, second elements, all the way to the very last elements. Statically, they are simply just students, statically, okay? So static type, students. Static type, also students. This one here, statically, also students. All the same. That's what we declare the array to be. And let's look at the methods we have, okay? So we have some method here. Let's say add RS. We want to add some new resident students, in which case we have a parameter RS, statically resident students. And then we have a variable assignments right here, which is the one I put here. The question is, does this particular variable assignments compile? That's a question, right? Which is not too bad because we're still having a variable assignment. You can also figure out the static type for the left-hand side and the right-hand side quite easily, which I already prepare you for, right, from the first question. Does this compile? Yeah, Daniel, go ahead. Because?
All the elements in the students array are ancestors.
Ancestor of the static type over here. Exactly. Good, good. I'm pretty sure your fellow student agree. So here, RS, we know that statically is resident student. You can see just from the parameter declaration. The static type is resident students. And for SS at a particular index C, we know that it should be a student as well, right? So something we just said. That one, static type is also it's actually students, beg your pardon. So now the question is, can RS fulfill students? Yes, because RS is a descendant of S. So this will compile. Yes, because RS descendants of students. Okay, so far so good. The final question before we do more example. Let's now try to generalize that a little bit, okay? Slightly. Let's now consider this line. Let's say we already got some instance of student management system. Okay, that's really this class right here. Okay, so let's say this is properly initialized. The static type over here is student management system, which declares add RS. So now we are considering this method here. Add RS and add RS. And we're asking the following question. In order for this particular method call, which will take some arguments O, which we assume is declared somewhere else. In order for this method call to compile, what should be the condition? I'll write it down first. In order for this method call to compile, what should be true about O? What should be true about the arguments O? Okay. Okay, this question here is critical because we're going to use that to judge about all the other method call. Go ahead.
As soon as O meets the key at
you're actually right, but when you say O is a descendant of, that's not exactly right. O is an object. You cannot say an object is a descendant of something. You gotta say O static type or O dynamic type. Which one? Because we'll talk about compilation, right? That's very good, you know. All right, so we know that we are calling this method. So let's now think about, again, call by value. So think about right here, call by value. So call by value tells us we got RS assign O. Okay, we know that RS statically was declared as resident students. Static type is resident students. So now the condition for this thing to compile is O static type must fulfill resident students, right? Good. So here, the static type must fulfill RS or descendants of it. It should be a descendants of. Right? So that's the final answer for this one here. Okay? Just watch out for the reasoning over here. It's very important for you to start with the method call and look at how the call by value is really implicitly executed, and then try to see how the rule of substitution is really applied. All right? Let's now do some example together. Okay? First of all, let's start with this. So given that we already got students array, statically we know that it's students, each elements. And then we're just going to look at some tester. Okay, let's say we got different variables here. Let's say we got S1, S2, S3. Okay, so far you can see statically S1, S2, S3, they're all students. As far as compilation concerned, we only look at students. But dynamically you can see they're different, but it's not our concern. We only worry about compilation for now. And then we got RS, which has a static type, resident students. Also we got NRS, static type, non-resident student, right? So we got these many variables. And we got some new objects, SMS, right? Initialize it properly so we can make some method call. Okay, so now we're gonna talk about different method call right here. Okay, let me just switch to iPad here. Okay. Let me remind you very quickly, so you can see all these have static type students. RS, resident students, NRS, non-resident students. And we are basically calling this add RS right here. So add RS, this one here. So we talk about the same method being called right here. Which we somehow did some exercise already, right? So now the question is, determine whether each line should compile or not. Let's say 1, 2, 3, 4, 5. Careful, because of course I can give you some hints. In order to judge, you must understand about the variable assignments accordingly for call by value. And the order must be right. And then think about the static type for the two sides. And then you should be able to decide. How about number 1? Should it compile? Number 1. Where we got static type for S1, the argument something. Accordingly, we also have the method call, the method being called right here at RS. Static type for parameter is resident student. We got everything we need. All you need to check will be which one should be the left-hand side for the variable assignment and which one should be the right-hand side, and to see if the normal rule of substitution will actually be satisfied. Right? Daniel, I'll have before that, if you don't mind. Go ahead, please. It's okay to be, well, I'm sure you'll get it right. Go ahead. Should this compile?
No.
It wouldn't compile, I agree, but can you put some explanation for that?
It wouldn't talking about because the right-hand side static type would be resident student and the left-hand side would be student. So resident student is not a descendant.
I think I like your explanation, but you said it kind of opposite way. Yeah. But that's okay. I know exactly what you mean. Let me repeat it, all right? I think your fellow student definitely on the right track. It's definitely good to try, okay? So let's see. Look at this method call here, and also the method being called right here. We try to connect them right here using call by value. Call by value will be RS is assigned S1. Right? If you're not really feeling that comfortable just by thinking without sketching it out, that's okay. Just sketch it out. It might take some time. And we know that accordingly, RS static type is resident students. S1 declared to be students. So now we're asking, can student fulfill RS? Nope, it cannot. So not going to compile. Okay, it's not going to compile because the arguments static type, which is students, cannot fulfill the static type of the parameter, which is resident students. Okay, that's a complete explanation. How about number 2? Compile? You think so? You will compile? Or you will, sorry, when I say number 2, okay, just make sure. That's my fault. I should have made it more clear. Is this going to compile?
Yeah.
No. Well, actually, think about it this way. S1 and S2, they have the same static type. If somehow S1 didn't compile, if you apply S2, you wouldn't compile either, right? The explanation would be similar. So this one here is going to be S2 and RS. If you do RS is assigned S2, you'll work out. It's not going to compile. All right? Guys, that's good. All right? This one also is not going to compile. S3, similar reason. Okay, how about number 4? Go ahead. It will compile. Okay, so now let's see this. It's going to be RS and RS over here. Don't get confused. They have different name scope. Okay, right here. So why don't I say, let's say this is an argument RS, and this is a parameter RS. So this one boils down into RS, the parameter is assigned the argument RS. So the RS over here has a static type, resident students. Okay, static type, resident students. And parameter is here, resident students. And resident student, descendant class of itself. So it will compile. That's good. Finally, how about this? Number 5. Okay, if you think no, that's definitely on a good track. All right, this one here, let's do it together. It's not going to compile. This one here, NRS, is going to boil down into RS parameter is assigned NRS. NRS declared to be non-resident students. So the static type is non-resident students. RS, the same parameter, static type is RS. Okay, so now the question is, can NRS fulfill RS? No, it cannot. They have nothing to do with each other. They're not descendants, right? So it's not going to compile. So now let's do a mini conclusion. What does that mean? You can see out of all the possible arguments we have put, given this particular method, the static type for the parameter is actually RS, but only this one here can compile. And that one there has a static type, resident student. What does that mean? Whenever you declare the parameter of certain static type, you can only pass an argument whose static type can fulfill this expectation, which means it has to be a descending class. I'll write it inside down, right? Okay. For a method call to compile, the arguments static type must, you can think about either fulfill the expectation of the parameters static type, which is resident students. Accordingly, you can think about the argument static type must be a descendants of resident students in this case. But how many descendant students, how many descendant class do we have for resident student? Just itself. It's already at the bottom of the hierarchy, right? All good. Let's do a final part and then we're done, okay? Only 1 minute or two, okay? Now this one here is interesting, okay? We're now talking about different method. Let's say add students. So now you can see that students, different static type for the parameter, right? And then you can see that we call add students all here. So let's say all these. Are they going to compile? Somehow, to really solve this one a little bit more quickly, you got to think about somehow I put some very high up class students as a static type for the parameter. According to what I just said as an insight over here. What can be the static type for the arguments in order to make calling this method compile? The argument must have a static type, a descendants of these students. Students is already at the top of the hierarchy. Everything is a descendants. So that means S1, S2, S3, RS, NRS, they're all of static type that's in the descendants of students. They're all going to compile. Okay, I'll write down this, give me 30 seconds, and then we're done. Okay, just want to write down the insights for you so you can study that later. Okay, because add students has the parameters static type the top of inheritance hierarchy. Any arguments whose static type is a descendants will work. Is a descendants of students will compile. All right, guys, think about it. I know it's a bit kind of overwhelming about many things to be covered today, but that's something we should know in order to move on to the next stage. Okay, study this, and then on Wednesday, I think I will still need to cover something more, but if you got any question about the test, you can drop by office hour, or I can stay a little bit longer after class. Okay, take care. I'll see you on Wednesday.